In the cold expanse of space, something impossible was happening. The object designated 3I Atlas, the third confirmed interstellar visitor to our solar system, was defying the fundamental laws of physics that govern every comet humanity had ever observed. And astronomers around the world were struggling to explain what their telescopes were showing them. Picture this. You are standing in a field on a dark night, holding a garden hose. You turn on the water and start spinning in circles. What happens to the stream of water? The curves, right? It spirals outward in a beautiful arc because you are rotating while the water travels away from you. This is not just a quirk of garden hoses. This is physics. This is the same principle that governs everything from hurricanes to spiral galaxies. When something rotates while ejecting material, that material curves. Always, without exception. Or so we thought. The object hurtling through our solar system in late 2025 was about to challenge that assumption in the most dramatic way possible. 3I Atlas, named after the telescope survey that discovered it, had been confirmed as an interstellar visitor, an icy wanderer from another star system passing through our cosmic neighborhood. It exhibited all the classic signs of a comet. It had a coma, the fuzzy cloud of gas and dust that surrounds the nucleus. It had jets, or streams of material blasting off its surface as the sun's heat caused buried ice to vaporize and explode outward, and it was spinning, rotating once every 16.16 hours, a fact confirmed by multiple observatories tracking its brightness variations as it tumbled through space. But there was a problem. A massive, glaring physics breaking problem. The jets were perfectly straight, and they should not have been. Let me explain why this is so strange, so fundamentally wrong, that it sent ripples of confusion and excitement through the astronomical community. When a comet gets close to the sun, the intense heat does not warm it evenly. Instead, specific spots on the nucleus heat up more than others, usually the areas directly facing the sun. Beneath the surface, pockets of ice start to boil, not gradually but explosively. The ice does not melt. It sublimates, transitioning directly from solid to gas. This creates enormous pressure, and eventually the surface cracks. When it does, a jet of gas and dust erupts into space like a geyser, traveling at incredible speeds, typically around 400 to 500 meters per second. Now here's the key part. These jets do not come from the entire surface of the comet. They come from specific vents, specific weak spots or fractures in the crust. Think of them as volcanic vents on Earth. But instead of lava, they are shooting out clouds of water vapor, carbon dioxide, and dust particles. And because the comet is rotating, these vents are constantly changing their orientation and relative to the sun and to us observing from Earth. Imagine you're on a merry-go-round and you're spraying silly string as you spin. By the time the silly string travels a few meters away from you, you have already rotated several degrees. The stream does not go straight. It curves into a spiral pattern. The faster you spin, or the longer the string travels, the more pronounced the curve becomes. This is exactly what happens with cometary jets. Astronomers call it rotational smearing. The jet material leaves the vent in one direction, but because the vent is turning as the nucleus rotates, the path traced out by successive particles creates a curved, fan-shaped structure. This effect is not subtle. It is mandatory. It is a direct consequence of combining rotation with outflow. For 3I Atlas, the numbers were staggering. Astronomers had measured its rotation period very precisely through coordinated observations in July and August of 2025. 16.16 hours, plus or minus just 1/100th of an hour. That is rock-solid data. Then, in November, high-resolution imaging revealed jets extending over 1 million kilometers from the nucleus. 1 million kilometers. That is more than twice the distance from the Earth to the Moon. These were not little puffs of gas. These were immense, sustained outflows stretching across a significant fraction of space. So let us do the math. If the gas particles in the jet are traveling at a typical cometary outgassing speed of about 400 meters per second, how long does it take them to travel 1 million kilometers? You divide the distance by the speed. 1 million kilometers is 1 billion meters. Divide that by 400 meters per second, and you get 2.5 million seconds. Convert that to days, and it comes out to roughly 30 days. 30 days for the gas to travel trailed from the nucleus to the far end of the observed jet. Now, if the nucleus is spinning with a period of 16.16 hours, how many full rotations does it complete in 30 days? 30 days is 720 hours. Divide 720 by 16.16, and you get approximately 45 rotations. 45 complete spins. Think about that. If you were on that merry-go-round spraying silly string and you spun around 45 times while the string was still traveling outward, what would the pattern look like? It would be a chaotic, tangled mess. It would be smeared across the sky in a broad, diffused spiral. There is no way, absolutely no way, it would remain a tight straight line pointing in a single fixed direction, but that is exactly what 3i Atlas was doing. The jets were straight, perfectly, impossibly straight, no curvature, no smearing, no spiral pattern, just a single laser-focused stream of material extending over 1 million kilometers, as if the source had not moved at all during the entire 30-day period. This is the jet kinematics paradox. The object is confirmed to be spinning rapidly, yet its jets behave as if it is not spinning at all. It is like watching someone on a spinning merry-go-round spray silly string in a perfectly straight line, despite rotating 45 times. It should not be possible. It violates everything we know about rotating bodies and outgassing mechanics. Naturally, scientists tried to find explanations. They had to. Extraordinary claims require extraordinary evidence, and before anyone starts talking about alien probes or advanced technology, you have to exhaust every possible natural explanation. So let us walk through the attempts to rescue this paradox using conventional cometary physics. The first idea was polar venting. If the active vent, the spot where the jet is coming from, happens to be located exactly at one of the rotational poles of the nucleus, then the rotational velocity at that point is zero. Think of a spinning top. The tip is not moving sideways, even though the rest of the top is whirling around. If the jet originates from the pole, it would not experience the rotational smearing effect, and it could remain relatively straight. Okay, that sounds reasonable. But there is a catch. Actually, several catches. First, for the vent to remain active and produce a continuous jet over 30 days, it needs to be heated by the sun. The sun's heat is what drives the sublimation. For a polar vent to stay illuminated and active for such a long time, the rotational axis of the comet, the imaginary line running through its poles, would need to be pointing almost directly at the sun. Not just roughly in that direction. Almost exactly. We are talking about an alignment precision measured in degrees, maybe even less. But here's the problem. Comets do not just spin, they also wobble. They tumble. They experience torques from the jets themselves, which can push and twist the nucleus over time. Maintaining a perfect pole to sun alignment for 30 consecutive days is kinetically fragile. It is like trying to balance a pencil on its tip. Even the tiniest disturbance would knock it off alignment, and suddenly your polar vent is no longer a polar. It starts rotating into and out of sunlight, and the jet would begin to curve or flicker on and off. The statistical likelihood of such a perfect alignment happening by chance and then remaining stable for a full month is vanishingly small. It is not impossible, but it is stretching the boundaries of plausibility. The second natural explanation involves something even more extreme. What if the rotation of the nucleus itself had changed? What if just before the jets were observed, something happened to slow down or even stop the spin? This is not entirely science fiction. Astronomers have observed cases where cometary outgassing produced strong enough torques to alter the rotation rate of the nucleus. There is a famous example, Comet 41P Tuttle-Giacobini-Creesack. Observations showed that its rotation period increased dramatically, meaning it slowed down because of asymmetric outgassing. The jets were not firing evenly from all sides, so they acted like tiny rocket engines, pushing the nucleus and changing its spin. For 3I Atlas, you would need something similar but far more extreme. You would need the object to experience a catastrophic rotational dampening, a sudden and dramatic slowdown from its confirmed 16-hour spin period down to nearly zero rotation, all within the days or weeks before the November observations. This would require an absolutely colossal amount of mass loss and a very specific configuration of jets to produce the right torque in the right direction. But if that much mass was being blasted off asymmetrically, you would expect to see other effects. The nucleus might fracture. It might break apart entirely. Comets are not solid rocks. They are often described as dirty snowballs, fragile aggregates of ice and dust held together by weak gravity and frozen volatility. Subjecting such an object to the kind of violent, sustained outburst needed to stop its rotation would likely tear it apart. Yet 3I Atlas showed no signs of fragmentation. It remained intact, stable, and the jets stayed straight. So the natural explanations, while theoretically possible, require stacking multiple low probability events on top of each other. Perfect polar alignment, sustained stability, or alternatively, catastrophic rotational changes without structural collapse. Each scenario on its own is already pushing the limits of what we expect from a typical comet. Combined, they start to feel less like science and more like wishful thinking. And that is when the other explanation enters the conversation. The one that makes people uncomfortable. The one that sounds like science fiction, but fits the data almost too well. What if 3I Atlas is not a comet at all? What if it is a spacecraft? What if those perfectly straight jets are not passive sublimation vents, but controlled exhaust plumes from an active propulsion system? If you are an engineer designing a probe to travel between star systems, you need precise control over its orientation and trajectory. You cannot just let it tumble randomly through space. You need what is called an attitude control system, a set of small thrusters or reaction wheels that can adjust the spacecraft's rotation and keep it pointed in the right direction. In modern spacecraft design, these are called reaction control systems, or RCS. An RCS works by firing tiny bursts of gas or rotating internal flywheels to counteract unwanted spin or drift. If your spacecraft is tumbling, the RCS fires thrusters to stop the tumble. If it is drifting off course, the RCS nudges it back. It is a closed-loop feedback system, constantly measuring the spacecraft's orientation and making tiny corrections to keep it stable. Now imagine 3I Atlas is such a craft. It is spinning, perhaps due to some ancient impact or imbalance, at a rate of once every 16 hours. But its propulsion system, maybe a main engine or a set of directional thrusters, needs to fall in a specific fixed direction to adjust its trajectory or slow down as it approaches the sun. The RCS would automatically compensate for the spin. It would fire counter torques to hold the exhaust nozzle steady relative to the stars, nullifying the rotational effect. The result? A perfectly straight jet, utterly unaffected by the underlying spin of the hull. This would explain everything. The straight jets, the sustained direction, the lack of smearing over 1,000,000 kilometers and 45 rotations. It would not be a violation of physics, it would be engineering. Active, intelligent, continuous additive control. The kind of system you would expect from a probe designed to travel across light years and still function when it arrived. Of course, this raises 1,000 more questions. Who built it? When? Why is it here? Is it still active or is it a derelict? Its systems running on automatic, mindlessly executing commands programmed millennia ago. But before we get ahead of ourselves, we need to look at the rest of the evidence, because the straight jets are just one piece of a much larger puzzle. And when you put all 12 anomalies together, the picture that emerges is even stranger than anyone imagined. The straight jets were strange enough, but as astronomers dug deeper into the data streaming back from observatories around the world, they began to realize that 3I Atlas was not just breaking one rule of cometary physics, it was breaking nearly all of them. And the anomalies were piling up in ways that made even the most open-minded scientists uncomfortable. Let us start with the mass problem, because it is perhaps the most statistically damning piece of evidence in the entire puzzle. When 3I Atlas first approached the inner solar system in the early 2025, telescopes detected something that did not initially seem perfectly normal for a comet. The object was not following a purely gravitational trajectory. It was experiencing what astronomers call non-gravitational acceleration, a tiny but measurable push that could not be explained by the sun's gravity or the gravitational pull of any planet. This is the classic signature of a comet. As ice on the surface sublimates, the escaping gas acts like a rocket engine, giving the object a small kick. It is the comet equivalent of a leaky balloon zipping around a room. Nothing unusual there, except the numbers did not add up. When you observe non-gravitational acceleration in a comet, you can work backwards to figure out how much mass it is losing and how that relates to the size and mass of the nucleus itself. The acceleration depends on three things. First, the rate at which mass is being expelled. Second, the velocity of that expelled material, which for cometary gas is typically around 400 to 500 meters per second. And third, the inertia of the object itself, its resistance to being pushed around, which depends on its total mass. The relationship is straightforward physics. If you know two of those variables, you can calculate the third. For 3I Atlas, astronomers had excellent astrometric data. Over several months from May through September 2025, telescopes captured more than 4,000 precise positional measurements. That is an enormous data set, and it allowed researchers to place very tight constraints on the non-gravitational acceleration. The result? Any deviation from a pure gravitational orbit had to be smaller than 15 meters per day squared. That is incredibly small. It means the object was barely being pushed at all, but at the same time other observations were showing massive outgassing activity. Spectroscopic measurements revealed that the comet was losing substantial amounts of gas and dust. Conservative estimates suggested that during its closest approach to the Sun, its perihelion passage, 3I Atlas would shed approximately 10 to 13% of its total mass over the span of just 1 month. 10 to 13%. That is not a gentle leak. That is a violent, explosive shedding of material. For a typical small comet, that kind of mass loss would produce enormous acceleration, easily detectable in the astrometric data, but 3I Atlas showed almost none. The only way to reconcile these two observations is to assume that the object is far more massive than it appears. If the nucleus has a huge amount of inertia, then even substantial mass loss will not accelerate it very much. It is like trying to push a cruise ship with a leaf blower versus pushing a canoe. The same force produces vastly different accelerations depending on the mass. So researchers crunched the numbers and came up with a required mass. To suppress the non-gravitational acceleration were the observed levels, while still accounting for the detected outgassing, 3I Atlas would need to have a mass exceeding 33 billion tons. 33 billion tons. That translates to a solid nucleus diameter of at least 5 kilometers, possibly larger depending on its density and internal structure. Now let us put that in context. The first confirmed interstellar object, one Oumuamua, which visited us in 2017, was estimated to be somewhere between 100 and 1,000 meters across, with a mass perhaps in the millions of tons. The second interstellar visitor to Borisov, detected in 2019, was a more conventional-looking comet with an estimated nucleus diameter of less than 1 kilometer and a mass in the hundreds of millions of tons. Both of those objects fit comfortably within the expected size distribution for interstellar wanderers based on models of planetary system formation and ejection dynamics. But 3I Atlas, if the mass estimate is correct, would be 3 to 5 orders of magnitude more massive than those previous visitors. That is not 3 to 5 times larger. That is 1,000 to 100,000 times more massive. It would be an absolute giant among interstellar objects. And here's the problem. Statistically, you should not find the giant first. Size distributions in astronomy follow a power law. There are many more small objects than large ones. For every massive comet, there should be thousands or tens of thousands of smaller ones. Based on the discovery rate of interstellar objects and the sensitivity of our surveys, astronomers calculated that the probability of detecting an object this massive before finding hundreds of thousands of smaller ones is less than 0.1%. It is not impossible. It is just extraordinarily unlikely. It is like walking into a forest and immediately tripping over the largest tree in the entire woodland before you have seen a single sapling. And then there is the composition issue, which adds another layer of strangeness to an already bizarre object. When astronomers analyze the light coming from a comet's coma, they can identify which molecules and atoms are present by looking at their spectral signatures. Different elements and compounds absorb and emit light at very specific wavelengths, creating unique fingerprint. For 3I Atlas, observations using instruments like the Very Large Telescope in Chile and the James Webb Space Telescope revealed something unexpected. The coma was rich in nickel, not just a trace amount, but a significant detectable quantity. And oddly, there is very little iron. This is strange because in natural astrophysical environments, nickel and iron almost always occur together. They are formed in the same nuclear fusion processes inside dying stars, and they condense together in the protoplanetary disks where comets are born. Meteorites that fall to Earth, which are fragments of asteroids and primitive solar system material, contain both nickel and iron in predictable ratios, typically with iron being the dominant metal by far. Nickel is usually just a minor component, making up 10 to 20% of the metal content at most. But 3I Atlas seem to have nickel without the corresponding iron, or at least with iron levels so low that they were undetectable. Some researchers pointed out that this nickel dominance, while unusual, is not completely unprecedented in comets. Cometary composition is highly variable, and different formation and environments can produce different elemental abundances, but others noted that a nickel-rich iron-poor signature is characteristic of certain industrial alloys. On Earth, we create specialized nickel alloys for applications where high strength, corrosion resistance, and thermal stability are required. Think of jet engines, spacecraft components, or chemical processing equipment. These alloys are engineered to have specific properties. And one way to achieve that is by controlling the nickel to iron ratio. The fact that 3I Atlas displayed such a ratio naturally, without any industrial processing, raised eyebrows. And then there was the water problem. Comets are often called dirty snowballs because they are primarily composed of water ice mixed with dust and other frozen volatiles like carbon dioxide and methane. When a typical comet from our solar system becomes active, water is usually the dominant component of the outgassing. Spectroscopic observations of comets routinely show that water vapor makes up 80 to 90% of the gas being released. It is the signature molecule of cometary activity, but 3I Atlas was different. Observation by multiple telescopes, including detailed spectroscopy by the James Webb Space Telescope, revealed that water made up only about 4% of the total mass being ejected. 4%. The coma was instead dominated by carbon dioxide, with a carbon dioxide to water ratio of approximately 8 to 1. That is one of the highest ratios ever measured in any comet, interstellar or otherwise. To put it bluntly, 3I Atlas was not behaving like a typical icy comet. It was behaving more like a carbon dioxide iceberg with just a thin frosting of water ice on the surface. Now, there are natural ways this could happen. If the object formed in a very cold, carbon dioxide-rich region of its parent star's protoplanetary disk, it might naturally have this composition. Or if it had been wandering through interstellar space for billions of years, repeated exposure to cosmic rays and starlight could have sublimated away most of its surface water, leaving behind more refractory, harder to evaporate materials like carbon dioxide ice. Some scientists suggested that the detected water might not even be coming from the nucleus itself, but from tiny grains of ice being ejected into the coma and then sublimating at a distance from the core. But there is another interpretation. If 3I Atlas is not a natural comet but a technological artifact, the low water content makes perfect sense. The bulk of the structure would be made of metals, ceramics, or other durable materials capable of surviving an interstellar journey. The observed outgassing might be residual volatiles, perhaps propellant from a fuel system or thermal regulation fluids leaking from internal reservoirs. Water in small quantities could be present as coolant or as contamination frozen onto the exterior during its long voyage through space. The carbon dioxide might be exhaust from a power generation system or waste gas being vented. In this scenario, the strange composition is not a puzzle. It is exactly what you would expect. What made all of this even more perplexing was the structural integrity of the object. Remember, 3I Atlas was losing 10 to 13% of its mass in a single month. For a natural comet, that kind of rapid, sustained outgassing usually leads to fragmentation. The nucleus cracks apart, chunks break off, the whole thing disintegrates into a cloud of debris. This is not rare. Astronomers have watched dozens of comets break apart as they approach the sun. The forces involved, thermal stress, pressure from subsurface gas buildup, and mechanical weakness from the porous structure, are simply too much for many comets to withstand. But 3I Atlas remained intact. High-resolution imaging from the Hubble Space Telescope and other instruments showed no signs of fragmentation, no companion chunks, no spreading debris field. The object held together. If it truly had a massive consolidated nucleus with a diameter of 5 kilometers or more, that would explain the structural stability. Such a large body would have enough internal gravity and structural cohesion to resist the stresses of outgassing. But again, that brings us back to the mass problem and the statistical improbability of such a giant being the third interstellar object ever discovered. Every piece of data seemed to push the interpretation in one of two directions. Either 3I Atlas is an extraordinarily rare natural object, a massive interstellar comet with a bizarre composition and a perfectly stable structure, defying the odds at every turn. Or it is something else entirely, something designed to be robust, something built to travel between stars without falling apart, something with controlled propulsion and an engineered exterior. And the deeper astronomers looked, the harder it became to dismiss that second possibility. So far, we have examined the impossible straightness of the jets and the bizarre mass and composition and profile, but those were not the only oddities. When you look at where 3I Atlas came from, how it moved through the solar system, and how it appeared to our telescopes, the strangeness only deepens. Some of these anomalies seem subtle at first, mere statistical curiosities, but when you add them all together, they form a pattern that is difficult to ignore. Let us begin with the trajectory itself. When an object enters the solar system from interstellar space, it can arrive from any direction. The galaxy is vast, and ejected comets or rogue planets wander in all directions with no preferred orientation. Most of the stars in our galactic neighborhood orbit the center of the Milky Way in roughly the same plane, the galactic disk. But individual objects that get kicked out of their home systems tumble through space with random trajectories. So when we detect an interstellar visitor, we should expect it to come from a random angle, slicing through our solar system at any inclination. The solar system itself is relatively flat. All the major planets orbit the Sun in nearly the same plane called the ecliptic. This flatness is a relic of the solar system's formation from a spinning disk of gas and dust 4.5 billion years ago. Objects that formed here, asteroids, comets, planets, all mostly stick to that plane, with inclinations typically less than a few degrees. But interstellar visitors should not care about our ecliptic. They were not born here. They have no memory of our protoplanetary disk. They should arrive tilted at steep angles, diving down from above or swooping up from below. But 3I Atlas did not do that. Its trajectory was highly aligned with the ecliptic plane. When astronomers calculated the orbital elements, they found that the inclination of its path relative to the ecliptic was remarkably small. It came in along the plane of the solar system, moving through the same flat region where all of our planets live. The probability of this happening by random chance, given the infinite possible approach, angles from interstellar space, was estimated at just 0.2%, one chance in 500. Not impossible, but certainly raising eyebrows. It is like tossing a coin into the air and having it land perfectly on its edge instead of heads or tails. It can happen, but you would probably want to take a closer look at that coin. And then there was the timing. An interstellar space is incomprehensibly vast. Even the nearest star system, Alpha Centauri, is more than 4 light years away. That is over 40 trillion kilometers. Objects drifting through that emptiness take millions of years to traverse the gulf between stars. When one finally wanders into our solar system, the odds of it arriving at a moment when the planets happen to be arranged in any particular configuration are astronomically small. The planets are constantly moving, orbiting the Sun at different speeds. Jupiter takes 12 years to complete one orbit. Mars takes about 2 years. Venus just over half a year. At any given moment, they could be scattered anywhere along their respective orbits. But when 3I Atlas made its closest approach to the Sun in the late 2025, 3 of the most prominent planets, Mars, Venus, and Jupiter, were positioned in a relatively tight grouping in the sky as seen from the comet. They were not perfectly aligned in a straight line, but they were all within a fairly narrow arc, close enough that a spacecraft passing through the inner solar system could potentially observe all three in a single sweep. Astronomers calculated the probability of this planetary configuration coinciding with the arrival of a random interstellar object. The odds came out to approximately 0.005%. That is 1 chance in 20,000. Again, not impossible, just extraordinarily unlikely. Now, if you are a skeptical scientist, you might say, look, unlikely things happen all the time. The lottery has 1,000,000 to 1 odds. But someone wins eventually. And that is fair. But here is the thing. When you start stacking multiple low probability events on top of each other, the cumulative odds become vanishingly small. An ecliptic aligned trajectory is unlikely. A perfectly timed planetary alignment is even more unlikely. Straight jets that defy rotational physics. A mass that places the object in the extreme tail of the sun's distribution. A bizarre nickel-rich water-poor composition. Individually, each of these might be explainable as a fluke, a statistical outlier. But together, they start to look less like a series of coincidences and more like something intentional. And then there was the anti-tail. Most people have a mental image of what a comet looks like. A bright head, the nucleus and coma, with a long, sweeping tail streaming behind it, always pointing away from the sun. This happens because of solar radiation pressure. Sunlight, despite being massless, carries momentum. When photons from the sun strike dust particles in the coma, they push them outward away from the sun. Meanwhile, the solar wind, a stream of charged particles constantly flowing out from the sun, pushes ionized gas in the same direction. The result is that a comet's tail always points away from the sun, like a windsock in a constant breeze. But observers noted something strange about 3I Atlas. In addition to the expected tail pointing away from the sun, there appeared to be a faint jet or plume pointing in the opposite direction toward the sun. This sunward anti-tail was faint, difficult to see, and only visible in certain images, but it was there. And it should not have been. Radiation pressure does not push things toward the sun, it pushes them away. The solar wind does not blow inward, it blows outward. So how do you get a sunward anti-tail? In cometary science, anti-tails are not completely unknown. They can occur due to projection effects when the viewing geometry makes it look like the part of the tail is pointing the wrong way, even though it is not. Or they can happen if large, heavy dust particles get left behind along the comet's orbit, creating a trail that appears to extend in the opposite direction. But those explanations require very specific viewing angles and dust properties. For 3I Atlas, the sunward features seem persistent across multiple observations, suggesting it was not just a trick of perspective. The alternative explanation is that the sunward jet was real. And if it was real, it was not being produced by passive sublimation and radiation pressure. It was being actively expelled in that direction, perhaps by a maneuvering thruster, perhaps by a controlled vent adjusting the object's trajectory. In the context of the technological hypothesis, a sunward anti-tail makes perfect sense. Spacecraft performing trajectory corrections often fire thrusters in the direction opposite to where they want to go. If 3I Atlas was decelerating or adjusting its course as it approached the inner solar system, you would expect to see exhaust plumes pointing both forward and backward along its path. But the oddities were not limited to motion and geometry. The way 3I Atlas appeared to our telescopes was strange too. When astronomers measure the brightness of a comet, they look at how it changes over time as the comet moves closer to or farther from the sun. There's a predictable relationship. As the comet gets closer, the sun's heat increases, causing more ice to sublimate, which produces more gas and dust, which reflects more sunlight, making the comet appear brighter. This brightening follows a well-understood power law based on the comet's distance from the sun. Astronomers use this relationship to predict how bright a comet will become and when it will be most visible. For 3I Atlas, the brightness increase was extreme. It brightened faster than any other comet on record. The rate at which its apparent magnitude changed as it approached perihelion exceeded the predictions for even the most active comets. This suggested that whatever process was driving the outgassing was exceptionally vigorous, releasing enormous amounts of material in a very short time. Some researchers suggested this could be explained by the sudden exposure of fresh, volatile, rich ice as surface layers eroded away. Others wondered if the object was undergoing some kind of internal structural change, perhaps the collapse of subsurface voids releasing trapped gas. But there was another possibility. If 3I Atlas was not a passive comet but an active spacecraft, the rapid brightening could indicate the activation of an onboard system. Perhaps a power plant ramping up. Perhaps a propulsion system coming online. Perhaps thermal radiators beginning to glow as internal machinery heated up. In engineering terms, a spacecraft approaching the inner solar system might deliberately increase its reflectivity or activate external lights as part of an observational or communication protocol. And then there was the color. Astronomers measure the color of celestial objects by comparing their brightness at different wavelengths of light. A star that appears redder is cooler, one that appears bluer is hotter. Comets typically have a neutral or slightly reddish color because the dust in their comas tends to scatter sunlight in a way that preserves or slightly enhances the red wavelengths. But 3I Atlas exhibited a distinct blue coloration. In some observations, it appeared bluer than the sun itself, which has a surface temperature of about 5,700 degrees Celsius. This blue tint suggested that something unusually hot or energetic was happening in or around the nucleus. Now, some astronomers pointed out that specific gas emissions, particularly from ionized carbon monoxide or other molecules, can produce blue hues in cometary comas. It is not unprecedented, but combined with the rapid brightening and the high activity levels, the blue color added yet another layer of strangeness. It hinted at high energy processes, temperatures, or ionization states that go beyond typical cometary sublimation. If you wanted to design a spacecraft that could survive the harsh environment near the sun, you might use materials with high thermal emissivity that glow blue-white when heated. You might use plasma thrusters that emit blue ionized exhaust. You might have radiator panels that shine brightly in the blue end of the spectrum to dump waste heat into space. Finally, there was the polarization anomaly. Polarization is a property of light that describes the orientation of its oscillations. Normally, when sunlight reflects off a rough, dusty surface, the reflected light becomes partially polarized, with the degree of polarization depending on the angle between the sun, the object, and the observer. Comets typically show positive polarization, meaning the light waves are oriented perpendicular to the scattering plane. But 3I Atlas displayed extreme negative polarization, meaning the light waves were oriented parallel to the scattering plane. This was unprecedented. No other comet had ever shown such a strong negative polarization signature. It suggested that the particles in the coma had unusual optical properties, perhaps highly reflective surfaces or strange shapes, unlike the typical fluffy, irregular dust grains found in most comets. Again, this could be natural, the result of unique formation conditions in the object's home star system, or it could be artificial, the result of engineered particles, perhaps metallic flakes, or reflective coatings designed for thermal control or communication. When you lay out all these anomalies, trajectory alignment, planetary timings, anti-tail jets, extreme brightening, blue coloration, and polarization signature, the natural explanation starts to feel stretched, not broken, but stretched. Each individual anomaly can be explained away with enough creativity and statistical hand-waving, but collectively, they paint a picture that is difficult to reconcile with our understanding of how natural comets behave. And they fit remarkably well with the profile of an engineered object designed to travel between stars, observe planetary systems, and perhaps report back what it finds.